In this video, we're going to be using R to simulate ANOVA. So as a reminder, ANOVA is when we're comparing, or at least a one-way ANOVA is when we're comparing three or more groups to see if the distributions they come from might have different means. So we can kind of look at some different examples. So we're actually going to look at three different kind of sets of cases. The first is where we're simulating three groups that do come from the same distribution, so the same means. We're also going to do it again where we have three samples or three groups from distributions with different means. And then the third time we're going to do the same thing, but we're going to increase the standard deviation for each of these distributions that we're sampling from. So there's going to be a lot more noise. That's going to make it harder to kind of detect that signal. It's kind of harder to notice or detect confidently those differences because there's just a lot more variability than we would expect in general. So I'm going to be doing this in R here, and the first thing I'm going to do is just define these parameters. So we're going to start with three distributions with the same mean. We're going to have a constant standard deviation of 5, and we're going to do sample sizes of 30 for each. So I'll go ahead and kind of define that there. Next, I'm going to kind of write out these samples. So we're going to do x equals our norm with n, mu1, and SD as the parameters. Y is going to be the same thing, except it's going to be n mu2 SD, and Z is going to be our norm, n mu3 SD. So again, mu1, mu2, and mu3 are all the same, so you might be wondering, why am I doing this 3 times? Well, it's because we're going to be changing these numbers later, so we're going to go ahead and set it up as 3 different samples that have potentially 3 different parameters that we're going to be plugging in. All right, so we can define those, control enter, and those exist if we want to just kind of do this as we go. I guess I could just use the play button if it's the only thing in here, but I don't know, sometimes I do that. Okay, next we're going to put these together. So we're going to put these in one variable called response. And it's just going to be concatenate x, y, and z. And then, well, I guess I'll define that. And then we're going to make a group variable as well. So just to kind of label these as 3 different samples, we're going to make a group of 3 labels. We'll call them A, B, and C. So, but I want A, B, and C to repeat 30 times each since I'm going to have a length of 90. I'm going to have 90 rows here. So I need 30 A's. So I'm going to repeat A 30 times. Then I'm going to repeat B 30 times. Oops, goodness, okay. Repeat B 30 times. And then, let's see, I'm going to repeat C 30 times. And then I need a closing parenthesis on this. Okay. And then I'm going to put these in a data frame. I'm just going to call it df equals data.frame of response and group with my 2 variables. So this should create a data frame with 90 observations, 2 variables. We can see it here. Response and group are my 2 variables here. All right. Next, we're going to make a model. So model equals ANOVA, AOV, of response predicted from group. Data equals df is where we're getting these variable names from. And then we can just kind of look at this if we want. Summary of the model is going to be there. And so let's go ahead and see what happens. And we get an ANOVA table. Our F value is 0.11. Our P value is 89.6%. So that's pretty high, meaning that we found no evidence really of underlying differences. Our samples could very plausibly be coming from distributions with the same mean. So yeah, that seems to be the case. However, if I were to simulate this, a couple times, I'm going to get different results. So now my p-value is 34.9%. And honestly, if I did this enough, I'm eventually going to get a pretty low p-value by random chance here. I may not do it enough to get there, but remember that when we interpret a p-value, it's the probability of getting differences as far or farther than we did by random chance, if the null hypothesis is true. So by random chance, we can get, we can get differences that are unusual. We can get differences in that 5% zone 1 out of 20 times. So that's literally what it is. So yeah, you have to kind of be on the lookout for that. That would be a type 1 error to mistakenly reject the null hypothesis when it's actually true. But yeah, so just kind of an observation there that this is going about what we'd expect. Next, we can also extract the f value and the p value if we want. So now this is not super intuitive how you would get this, but it's going to be summary of model, and then you're first going to do a double bracket 1 to basically take the first entry of this list of 13. So this model produces a list of 13 entries. So I'm going to go to the first one, and then I'm going to extract the first row, 4th column for the f value, and the first row, 5th column for the p value. Again, it's not super intuitive why this is what you're plugging in. You can just kind of Google search usually when you need to extract a particular value and you don't remember where it is or how to find it. So I'm just going to grab those two things. And this will be helpful because we're going to be simulating this a bunch of times, so being able to extract f and p will be important later. We can also make a box plot of what we did here just to kind of look at our looking at our samples and trying to make inferences about what their distributions could be. But I certainly look at these 3 samples and say, hey, these seem like they could be coming from distributions with the same mean. There's not really any reason why they couldn't. Of course, if we simulate it again, we might get different results. But again, doesn't look like they're drastically different, but a little bit of difference here. But again, still kind of in that plausibility range that by random chance, this is not particularly unusual differences to observe. Okay. So let's go ahead and think about simulating this many times. What we want to do is look at the distribution of possible f statistics and p values that we would get when repeating this process a few thousand times, and just kind of thinking about what they represent and why they happen. So I'm going to make a function here first that accomplishes what this first half is doing. So I'm going to take this part right here, and I want to put this in a function. So I'm going to write sim ANOVA equals function, and my parameters are going to be mu1, mu2, mu3, and an SD. And on the inside, I'm just going to kind of repeat what I did earlier. So I'm going to have simulate x, y, and z, put them in a response variable, and then make a group variable as well. Oops. And then put them in a data frame. And I don't really need to call it df because the function will always just print whatever is your last entry anyway. So if this is my last line of the function, then this is what the function is creating. Okay, then I want to use this inside of a loop. So I'm going to write a loop here, and I'm just going to go to 5,000. So I'm going to do 1 to 5,000. And the reason I'm only going to 5,000 is just because this loop is going to take a little bit of time, and if I go much higher, we're just going to be waiting around. But I think this takes about maybe like 15 seconds, so that's not too bad. And so what I'm going to do is I'm going to call on this function, so simanova, and I'm going to set some parameters. So I'm going to start with just what we used before, even though we can obviously change this later if we'd like to. N equals 30, SD equals 5. And I'm going to call the results of this function df, because again, the function's creating a data frame. It's simulating these results and throwing them in a data frame. So I'm just going to call on the function and save it to df inside my loop and use that. Then I'm going to make a model, again, just like I did before. It's going to be response from group, data equals data df. And then I'm going to extract the f statistic and p value just like I did up here. But there's one little thing I need to add, and that's because I want to, what I want to do is make histograms of these distributions as we go. So I want to kind of collect them and iterate using the loop. So instead of just saving it under f, I need to save it under fi. So that way, what it's doing is it's kind of filling this up as a vector of f values for as long as my loop is. And the same thing with p here. I want to kind of iterate into p and save these p values that I get each time I run the loop. So since I'm doing that, I do need to define f and p up here. So I'm going to say f equals null, p equals null. So that way R knows what they are and they exist, and then I can just kind of fill them up as they go. Okay, I think that is it. And then the last thing I'll do is I'm just going to make a histogram of f. I'm going to make 30 breaks so we can see it clearly, and I want to do the same thing for p, so we can see that there. And assuming that I did everything right, this loop will run. It will take just a little bit of time, and then the histograms are going to pop up here in a second. And there they are. Okay, so let's start with the p-value histogram because I think this is kind of interesting. I think we've seen it before, but when we're simulating under the null hypothesis and extracting out p-values like this, then we should get a uniform distribution, right? Because if the null hypothesis really is true here, we're just as likely to have a p-value over here as we are over here. So it should be uniformly distributed across 0 to 100% for our possible p-values when we do this. And then our distribution of f values is going to be what's called the f distribution in this case, because if we're simulating under the null hypothesis, these are the different f values that we would expect to get and how often we should be getting them by random chance. So I mentioned that if the null hypothesis is true, then we should often see f ratios around 1. And as we get farther away from 1, the rarer it is to get that kind of an f ratio by random chance, because the f ratio, again, is the ratio of that between variance to within variance. So if the between variance is, just kind of random chance variation from group to group, then it should be equivalent to the average within variance that we're observing as well, and that ratio should be relatively close to 1. But when we're several magnitudes higher than that, that's when we start to get those low p-values and say this is pretty unusual to happen by random chance, that this is a little bit odd to see, suggesting that maybe there is some difference because this just doesn't happen very often, as we can see. So that's what happens if we simulate under the null hypothesis, but we can obviously simulate with different means. So let's say that I want to do means are 10, 12, and 14. How is that going to affect our results? So I can kind of run that up here, and we're going to do the same thing. And hopefully I've done everything correctly here. And we do definitely get some different results. So the first thing that we're going to notice is that our distribution of possible p-values is now heavily kind of centered over here on the left, meaning that we are correctly finding most of the time that this is unusual, that this doesn't make a lot of sense if the null hypothesis is true. I mean, every once in a while, maybe our sample means happen to be kind of close, but most of the time they are unusually far apart for the null hypothesis, as is truly the case going on here. You'll also notice that the distribution of possible f values that we're getting is no longer just the f distribution. Now we're getting a lot of f values around like 4 or 5, even up to 10 or 15, suggesting that most of the time, if this is really the case and we're randomly sampling from these distributions that have different means, we're going to be finding these f ratios that are kind of unusually high, thus producing these p-values that are unusually low. So yeah, that should make sense. One other thing, though, again, we talked about this idea of what if we increase the variation going on within each of our samples? What if the noise factor goes up quite a bit? So what if our standard deviation is 15? And so what I want to do first, let's go back up here to these box plots and just kind of look at what we were doing down there. So first I'm going to change the means. Then we're going to re-simulate this and get a new box plot. And you'll notice here, right, we get a little bit more distance between our groups, meaning that's a little bit easier to kind of detect that difference and reject the null hypothesis correctly. But what if we have a lot more noise? What if we're looking at a standard deviation of 15? How does that affect the comparison here? And you're going to notice here, it's not really obvious because the size looks the same, but you're going to notice that the scale, number one, is a lot different. The scale's a lot bigger. And as a result, the difference between sample means, even though it's the same like actual numeric magnitude on average, even though they're still centered around 10, 12, and 14, there's just so much more variability now that it's really hard to detect those differences confidently. And so what inevitably happens here is that the higher the noise level gets, the higher the standard deviation is. So if I even like go to something kind of crazy like 50, that's going to make it really hard to detect these differences in my samples. So I can do this again, and it's a little bit, actually we have some unusually low B group there, so maybe I should do it again to make a point. So if I do this again, again, it's just a little bit hard to see this because there's just so much variation. I mean, obviously, even my sample means have a lot more variation now as well, but it's hard to attribute this to underlying differences in the distribution rather than just, just the fact that there's just a lot of variability. There's a lot of within variability in comparison to how much between variability I'm seeing. All right, so with that in mind, I'm going to go back to our loop, but I'm going to change this to, I'm going to even bump this up. Let's do like 25 just to kind of make a point here. So when we have a lot more variability, I'm not going to get that same, p-value distribution that's all kind of around 0, 0.05. It's going to be a little bit more scattered. Yeah, so you can kind of see it's a lot harder to reject the null hypothesis, even though it really is different. There's so much noise that it's hard to detect that difference. Same with the F distribution here, is it looks a lot more like the true F distribution rather than kind of this, a lot of clusters of high F ratios that I would expect to see with differences like that.